Franklin Who. And today we are on StreamYard. And hopefully everyone got the message that we're trying to move our operations onto this new platform. So currently, though, I would like everyone to, if they can, to go on, say, youtube.naturalphilosophy.org if you wish to just watch. Or otherwise, if you'd like to speak, then go to live.naturalphilosophy.org, and you'll be able to be put on the screen just like Bill is over here. And I see we also have Dennis with us as well. So let's add you guys there. So how are you guys all doing? Hello, Dennis.
Hi.
And hello, Bill. Thank you for joining me in the live room. So I was for today. I was going to do kind of a mailbag kind of thing. Not unless you guys had any particular topics that you had in mind. So the standard here is that if you want to speak, I need you to basically turn on your camera and like wave at me or something. Because unlike Fuse, you could put a flag and then I could see that and then I would know you would want to speak. But here in StreamYard, we really don't have any such mechanism like that. So, so if you don't want to speak, then I need you to turn off your camera. And that also helps conserve bandwidth. But otherwise, if you do want to speak, I need you to go into the, if you're watching on YouTube, you need to go to live.naturalphilosophy.org, get yourself basically into my little green room here, my waiting room, and then turn on your camera and then, wave at me or something. So hopefully get my attention, right? But otherwise, turn off your camera, right? So Dennis, if you don't want to speak, then turn off your camera. Otherwise, if you do, then turn on your camera, and that way I'll know that you want to speak. All right. So we'll try and stick with that kind of standard, right? And and people can only hear you if I put you on the screen. All right. So we'll go with that. So let's see. We're going to do, like I said, a little mailbag thing here. And I got a response from Gary, who's a draft science. And let's see here. Let me share the screen here. There we go. And he's got a YouTube channel. He calls himself Draft Science. And so he was responding to the comments that I had made on polarization in one of the science chats. So that's great that he watches our videos, and he had some comments on how polarization works. So I thought he actually had a very good explanation for how the basic radio wave polarization works here. So he was explaining about how that if you have let's wait for the video to catch up here. So that if you have a antenna, that you need basically the same kind of antenna shape to receive the signal in the strongest possible way. So I totally agreed with that. I mean, that's exactly the way I think that the radio waves work. I'll see if I can play a little bit of this for you. Let's see here. Well, that's not right. That's programming in Visual Basic. I don't know how that happened. I think I pressed the wrong button there.
And that's polarization. And that it's more out of position the more time you give it. More time.
Okay, let's bring this back. I'm not sure why that got all the way over there. Okay.
Electrons producing photons in any one of a few directions.
Now, but he is pointing out an interesting thing, which is that radio waves and light waves are distinctly different phenomenon. Whoops, I think I did it again. I gotta stop pressing that button. The next video button rather than the pause button. Yeah, let's go back.
Of what I would say are dots, bands of dots.
So what he's pointing out here is that, if you have a stick antenna, that the things that are coming out of it, they look like these banding waves, right? So if you have that leftmost line is the antenna, then the waves would be like those other straight lines to the right.
That come off the antenna, blip, 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 and you're making the frequency deliberately. Light, you don't make the frequency deliberately. The electron takes care of that for you. You stimulate with some electricity, and you cause something to break down in some way where it excretes the photon. And again, the photon can not necessarily is very directional, where you could argue that the radio stuff is pretty directional. The antenna shoots it off, and yeah, it spreads off the antenna in these directions, all that stuff, but generally speaking. So there's a subtle difference between the two. One is caused by an atomic reaction in terms of an electron shooting. I would say electrons are also shooting in this case, but it's also much more sequential, much more whatever. All right, so you have those two.
Yeah, so I think this is an important distinction that he's making, that radio waves and light waves do seem to have, I would say, two very, very different characteristics, right? Although we consider that both of these are electromagnetic waves and we think they are the same basic fundamental thing, there is this difference that light seems to come off in discrete little packets. And that's because it's being created by an electron, which is like going from one level to another, which is a very discrete activity, versus a radio wave, which I think is a continuously created constant sinusoidal wave, versus light, which would just be like a single bump, right? That would be like, versus a whole bunch of just sinusoidal waves. I'm thinking that if you imagine you just take a rope and you just flip it up and down once, that's more or less what a photon of light would be. And that photon, I think, is highly directional. So it kind of goes out as like a particle. I mean, that I think this is where the wave particle duality thing is where that kind of comes in. Now, Draft Science, his thing is that he thinks that light is more like a particle. So, and I can appreciate that. Okay, so this is like his drawing of light as particles. So he's trying to draw on the top there, the conventional idea of magnetic and electric fields at 90 degrees to each other. And in the middle there, he shows just like one of those sinusoidal examples of what mainstream would consider light to be. And he's pointing out that in light, we've never really observed this sinusoidal thing. He's saying that it's not like the light gets, the fields get stronger, we observe stronger field, and it gets weaker field, and it gets stronger field. We never really observed that. So he feels that what you really have, you just have a clump of something. So he's done that with these circles here. So what you really have are like these circle things, and the distance between those circles is what we note as frequency. So he sees the light particle as literally, much more like a particle. And I can understand that. I mean, if it looks like a duck and sounds like a duck and quacks like a duck, well, it's probably a duck. And in the case of photons, a photon, it has like a finite distance. Like you have a gamma ray photon, you have a detector, it hits a specific part on the detector, it registers a specific amount of energy as if it were actually physically hit by a particle, like say a proton or an electron. The reaction is pretty much the same. So, but I would tend to argue that that's actually not the case, even though that we have a hard time measuring this, I would say, up and down field, and definitely we really can't measure the separate electric and magnetic field. I challenge people all over the place to say that, well, if there really is this transverse magnetic field, then why don't you just create a radio wave, and you can make it pretty long frequency, you can make it like a foot long, and then put a magnetic sensor along the path, and you can make it a standing wave so it doesn't move. And then you should be able to show me where the magnetic field is stronger and where the magnetic field is weaker, and prove to me that there is a time varying magnetic field in there. But no one's ever been able to do that. And I don't think you can, because I really honestly don't think it exists. That there's actually nothing magnetic or electric about the so-called electromagnetic wave, I would say. My hypothesis has always been that the electromagnetic wave has to be just like any other wave that we know about in mediums, which has to be a kind of compression wave. And there's really nothing transverse about that. So let's see here. I'm going to stop for a moment here. And I'm going to check to see whether anybody has any comments there. So if you have any comments, you can wave at me. Here, I'll check in with Bill. So, Bill, what do you think about that? I mean, there's this difference of opinion as to exactly what light is. Gary feels that it's more like individual packet of photons and that there really aren't any waves. And I feel, though, that that light is in fact just an ordinary compression type wave.
Well, my feeling is that you have to look at a broader picture to see how each of those approaches would fit in with the data. So, for instance, to give you an example, in my work, the electromagnetic field is the basis of the whole universe. And the only force is electromagnetic force. So then if you're going to have a wave, it has to be in the electric field. And if you have gravity, then you have to have something like a soliton so they can hit it out. And the soliton can get together and form structures that vibrate with mass. And so you've got all these things that you've got to explain. You've got to explain all the aspects of gravity. And the way I showed it, the approach is better, is I think any more gravitational phenomena than Newton's universal law of gravitation or Einstein's general theory of relativity. And I don't need matter and dark. And so it looks like you're making progress. But without taking bigger pictures, we don't necessarily get our theory to fit together with what we have observed in the past. So,
well, that would be a different. I mean, that this is an interesting point where you have your theories and they can predict, existing physical phenomenon. Although I have seen lots of theories which claim to basically do that. So that's not necessarily a really good indicator of truth, I would say. I mean, there are a lot of theories which say I can predict, the mass of the proton or the reaction of the electron or this or that or the other thing to a high degree of precision. And I've seen a lot of theories like that, and they all couldn't possibly be true. And the other thing is that we're not exactly sure how those things are derived. And just like in mainstream, you can make anything fit if you bang on it enough. I suppose it's more convincing if you can predict something which hasn't actually been experimentally measured. For example, say islands of stability or something like that. And then someone actually goes out and does an experiment and finds out that in fact that is true. Because otherwise, you can always do like a fit to the existing data. So I'm not terribly impressed by people who match, I say, existing data. But in this case, I think the most important difference is that you believe that the electromagnetic field itself is fundamental, which is, I think, a pretty hard thing to swallow because it's a really complicated thing. You've got the electric field, you've got the magnetic field, two fields that have to basically occupy the same space, and you're saying that that's fundamental, right? Now, how can something so complex be fundamental would kind of be my question to you, because I feel that those things definitely are not fundamental, and that they are based on more of a material based space rather than designating one of the most complicated things, which is the electric and magnetic fields, as fundamental. Since I think that the electric field is just another compression wave that's being emitted by electrons and positrons. That's all it is. So in that way, the electric field is not fundamental. And I put the fundamentalism on actually the particle itself. So the fundamental thing, I think, is the electron and the positron, and even those two things are exactly the same, except they ring out of phase. So, and I think people can agree that the electron exists. So I think that having your fundamental thing be the thing that even mainstream recognizes would be a more accurate picture of the world. So even though I can appreciate that you have made all of these predictions and things like that, and perhaps I think maybe the reason why they are so accurate is because you still have the right idea. It's just that you're basing it on the pre-existence of the electric and magnetic fields, and as long as you've got that right, then the rest of your predictions will be correct. So, and I'm kind of suspecting that's really the case. But just underneath your theory might be another physical explanation for the electric and magnetic fields themselves. So it may just be you're starting at a different level, I suppose. So, not necessarily, wrong or anything like that. But it could be that your fundamental electric and magnetic fields are actually a physical manifestation of some physical particles. So, and that's where I would go with that. Okay, but getting back to draft science, let's go ahead and I want to show some other things from that. Okay, so he was showing what he thinks is the polarization. Well, not polarization. He hasn't gotten into polarization yet, actually. Okay. So he is going to struggle with trying to explain what I thought what polarization was.
Thing that turns on a field of some kind in two ways, magnetic and electric. And they call that the transverse part. Other people would say the transverse part means it's doing this forward motion thing. Okay, that's one kind of movement. And then inside of that movement, it's doing some other up and down thing. Okay, and there's the transverse part. So, but whatever. We're just saying. So Franklin says, no, it's just like a sound wave.
Yeah, so that's an interesting point. He's trying to explain basically how difficult it is to actually describe the transverse component of an electric wave. You know, some people literally think it's like an earthquake wave and like something is literally moving up and down. But when you think about it in 3D space, it's really difficult to describe in any sensible fashion how that transverse wave works. Even in mainstream, there isn't actually anything that's moving physically up and down like an earthquake wave. What is transverse is the field strength. So you have like a north-south pole vector direction, and if you put a measuring instrument there, you should be able to see a stronger magnetic field pointing in that direction and a weaker magnetic field and a stronger magnetic field. It's a weakening and a strengthening of the magnetic field, and the only thing that is transverse is actually the direction, like the north-south direction or the positive negative direction of the field. So I've always felt that was just kind of a crazy kind of thing to imagine happening in free space, right? How can you have a magnetic field in the middle of nowhere, right? In the middle of space, interstellar space. You have a magnetic field where there aren't any charges to create those fields, and and similarly, you have an electric field where there aren't any charges to create those fields. So somehow these things are supposed to cooperate, and the collapsing electric field is supposed to create the magnetic field, and the collapsing magnetic field is supposed to create the electric field, but then they'd have to be out of phase to a certain degree, and they're not. They are totally in phase. So at some point, the electric field goes to zero, the magnetic field goes to zero, and when you got both of those fields going to zero, then there's just nothing left to keep this thing going, right? Everything goes to zero, and then it's gone. So, but Gary's trying to point out, kind of the ridiculousness of trying to describe even this transverse wave.
Which I still argue it's not a wave. Like Feynman, I'm arguing it's not a wave. So quit thinking in terms of waves. But anyway, so he's sort of arguing that it's not transverse, that it's just this. It's just a wave somehow. Some kind of wave that has a strength to it. I don't understand it. Just because we know that this is a different pressure here, here, here. And again, there's no evidence that photons, you can have like this much of a photon or, these little amounts. There's just every evidence that it comes in a clump, a quantum mechanical clump of energy. All right, so anyway, so let's get to the theory of what causes polarization. Now, Franklin's sort of implying some kind of polarization built into this amplitude or something. Like this amplitude represents the polarization.
Okay, so Gary is struggling with my explanation of polarization, and it actually has nothing to do with the amplitude. And in fact, it has to do everything to do with his first explanation about how radio polarization works. So I'm a little bit concerned that he completely understands how I explain polarization, which is it's shaped like the waves coming off of the original antenna. And it has nothing to do with, say, the amplitude. So I can understand why he would be confused about that. But really has nothing to do that. In fact, one of the strange things about the way I explain polarization is that you really can't explain it as being like a single wave phenomenon, because what it's relying on is actually the leading edge of a very, very large set of the waves. The waves come like ocean waves, right? The ocean wave is not just a single sinusoidal spot, like if you put a bobber in water, I guess that would be like a single spot. But you have to consider the entire ocean wave crashing on the beach, and you can see these things have a very distinct leading edge. And that leading edge is perpendicular to the direction of travel, right? So the only thing that you really need to describe a polarization is that you need to be able to describe some other vector direction that is perpendicular to the direction of travel. So like I keep on using like ocean waves as kind of an analogy, so you can see that it's the whole wave front that carries the polarization. Polarization cannot be carried on an individual wave, because in order to have a polarization, you need to have a whole bunch of waves all cooperating all together in a medium so that it can form this wave front, right? So I wanted to let Gary know that the actual concept of how I think polarization works is exactly what he initially explained back in the beginning, where he's explaining that you have an antenna, and the antenna puts out waves, and that those waves are better received by an antenna which is shaped exactly the same as your transmitter versus one which is vertically oriented. So in this particular picture, he's showing that if you have your transmitter on the left-hand side here, and you have your receiver on the right, and if it's a up and down line, just like your receiver, then all of the energy coming off of that transmitter is going to impact your receiver, and then you can like put a light bulb on that antenna and you can light it up. Now, if you put just basically a straight horizontal line like he has over here on the right, then really the only amount of radio information it's going to be able to intercept would be just that tiny little sliver in the middle, right? And this is how I see polarization actually working, right? It has got nothing to do with the amplitude. Yeah, that doesn't make any sense, but this is exactly how I feel polarization works. Now, I think, though, the trick is how do you consider polarization working with, light? Now, Gary has his alternate idea of how polarization works, and he considers the photons as being these little clumps, and he explains that as the atom emits these clumps, they're not exactly in a straight line, right? And he displays the polarization filter as basically like being like bars. Let's see here. And so as these not so straight streams of particles go through the bars, some of them are not going to make it through. Now, Now, like Gary, I'm not 100% sure if I quite understand the nature of his explanation here, because I can understand how that would just certainly block a certain fraction. You know, typically your losses through a polarization filter are on the order of about 50%. Right? Half the light gets lost. It gets blocked. And even as you pass through multiple filters, you know, you still lose some of the light intensity. I think I had a discussion with Carl about, you know, he didn't believe that that would happen, but there is a significant amount of loss at each level. Now, while I can understand there being a loss, I'm not 100% sure I understand how that actually then causes blockage in a polarizer that's oriented in the 90-degree direction, right? That really only explains why it like loses half of its intensity. But when I put it through one polarizer and then I put it through another polarizer that's in the opposite direction, then that completely blocks everything. But, you know, if the light were, you know, as Gary described, as being not, you know, 100%, you know, all in a straight line, then I'm not sure what orienting the bars at 90 degrees to the other bars is going to completely block everything at that point. So I think he's trying to explain that here. Maybe try.
There's taking advantage of is that the rays are not on a perfect line. They're a little bit oriented, and that's the nature of the polarization. And the longer the frequency, the more time there is for this orientation differential to be larger. Okay, so there's more variation. So X-rays would be really close to this line. You know, visible light would be a little bit wavy, you know, and radio waves would be a lot more wavy in terms of the out of alignment. So the first argument is that you have to have rays.
Okay, so I think I might understand what Gary is talking about here. So he thinks that the polarization angle is held on the difference in the spacing. So you have the particles. So let's suppose that you know, it's just like a spray of Nerf darts or whatever, and they occupy, you know, some finite like tube of space as you're firing them forward. But when you stick them through a polarizer, you basically are only picking out the objects that say fit through the slot, I guess, right? So, and the polarization direction is built out of the difference. So if you put it through a vertical slot, then you'd have like a bunch of particles that are basically stacked on top of each other as they come through. I mean, they wouldn't all come through at once, but they're kind of stacked on each other. And that kind of determines a polarization for that ray of light. And then if you put it through another polarizer that's going the 90-degree direction, then you'd basically only get like the one that's going right down dead center. That's the only one that'd make it through. And all the rest would be blocked. So I guess that's how he's seen how polarization works. And that's a little bit similar to how I thought polarization works, where that light can be considered like pencils, and polarizers can be considered to be like boards all lined up to make very, very long, thin slats, right? Because slats can also polarize, right? And that is certainly one way it could work. But I think I kind of understand where Gary is coming from.
The second argument is the
So he goes on to explain that. So I think that's the basics. But, you know, I would agree that there is definitely a difference with how polarization, it kind of needs to be perceived when you're dealing with light. So let's see here. Let me get back to my video here. So let me see if I can explain how I think even light polarization must work. Now, I think the key is that is what a polarizer is actually made out of, even for light, okay? Even for light, you have your polarized glasses here. And from what I understand, is that these are like the wire grids, like I had shown for the radio polarization. Their function is pretty much identical in that, you know, even something that looks like this, you don't see any wires, but chemically, they've created conductive paths in these, you know, polaroids, such that electricity can travel in one particular direction, right? And physically, they actually have polarizers that can be used for light, which are literally made out of very, very fine wires, right? And they work, all right? So I would say that the mechanism for the polarization between radio and light waves still has something to do with the waves being captured by a receiving antenna. So if the waves are captured by the receiving antenna, then they are blocked, basically, right? They're received, they're converted into electricity, and basically become heat. So now the question is what does that mean for an individual photon? So in an individual photon, we have an atom, and at some point, an electron gets knocked loose some distance away, and it comes back. It creates something, right? So I'm arguing that it creates like an individual wave. If you were to watch it on an oscilloscope, it go whoop, up and down, right? Now, I did have one other comment about Gary's feeling that light is a clump and that we've never really measured any of this time varying stuff. I would argue against that. I would say that we know that it is time varying for especially a radio wave, because we can stick an oscilloscope onto our radio antenna and we can observe the full up and down cycling of the wave, right? It doesn't come in a clump. It comes in continuous waves, and we can directly measure that. But like I said, that's kind of the difference between the radio wave and the light wave. I think that if you were to be able to do the equivalent thing with a light wave, you would see in the oscilloscope, you'd see one bump and then flat again. And the length of the bump would determine the frequency. So in an individual bump, you could measure just the frequency on an individual photon. And you know, the smaller the bump, the higher the frequency would be, and generally speaking, the higher the energy would be. But that doesn't really help with the explanation of how, like, you know, polarizing filters work, because I'm saying that there's actually a wave front that has an orientation that gets absorbed by the polarizing wires, right? So it cannot just be like an individual bump, because I think, like I told you, an individual wave cannot be polarized. You have to have at least a group of waves in your medium to describe something like an ocean wave crashing on the beach, right? So in order for me to explain that, I have to think that the photon can't in fact be just this one wave in any way, shape, or fashion, right? You've got a three-dimensional media, and within that three-dimensional media, you have a wave which is traveling through space, like say my hand, right? So my hand could be considered a photon, right? And so that thing is being generated, and as it's generated, the tips of my fingers, there's like four. Let's say there's like the media is it's at least 4 units wide, I guess, right? Within your media. So these 4 things can head out, but as they're generated, they can be at any angle, right? They could be this angle, they could be at this angle, they could be at this angle. But it's kind of like jets flying in formation, right? Kind of like the Blue Angels, right? They're coming in, they're all together. The polarization is determined by the unification of their wave fronts as they come through, right? So that determines the polarization angle of the light wave. And then as it hits the polarizer, then we use the same logic as we use for the radio waves, which is that if it hits if I have my jets here and they go and they fly into a vertical pole, all 4 of them are going to crash into the pole, and that's going to be maximum energy transfer, right? And just like the radio waves, that wave gets absorbed and it cannot pass through the filter. But if you have the radio waves going this way, and they're like jets hitting through a vertical pole, chances are they're all going to miss, right? Not unless it just hits directly head on to the one little pole that's just sitting there, right? So those will be allowed to pass, right? And then if you put it through another filter in the same direction, then they will continue to be allowed to pass through that, right? But if you put then another filter that is the opposite, the way that will absorb them, then they will be completely blocked, right? Since you will have eliminated all the other angles, that this direction is going to block you. So I think that's an interesting analogy. It's like, and I just came up with that. It's just like the Blue Angels. You have all your planes flying in formation. That direction is actually the polarization angle that the photon has. And like 4 planes, they have a fixed dimension to them, and they have a beginning and an end where they happen. But they're not a clump, right? And they do have, I would say, this maximum and minimum kind of behavior. And it would be kind of interesting to see whether someone could actually measure that. I mean, if you were to look at photons individually, I think that you would see that kind of behavior. And I think that, they do have some like ultra fast pulse experiments where they're doing things like measuring the speed of light and stuff like that. And when the charts do show that, it's not like a square wave. It's not just like there is a definite rise and a definite fall with that. And I think that would be consistent with the idea that we're dealing with a compression wave, that it takes a finite amount of time for the wave to rise and fall. So that's the way that I think that probably works. And so that would be my response to Gary. So, but once again, thanks for tuning in, and hopefully you kind of understand my viewpoint on this. I think I kind of understand your viewpoint a little bit, but and it's helped me kind of to like come up with this new analogy of like the Blue Angels, 4 planes flying in formation that actually delivers the polarization rather than say your idea, which is like, it's like planes, but they're like flying in all kinds of directions. But actually, maybe it's the same thing almost, kind of. But the nature of the actual blockage would be the same as you described for radio waves. It's just a matter of building the most effective receiver for the kind of waves that you're generating. So, in some ways, the four planes are just like your photons being not all exactly in the same place. But the important thing is that you get your photon, the individual waves, whatever is creating these things to line up so that you can describe this transverse polarization direction, which is perpendicular to the direction of travel, right? That is a fundamental thing that we have to deal with. So let's see here. Hope I didn't lose everybody. So I was kind of wondering, maybe we have some comments here. So let's go to comments here. So we have some people here. So we have a question from Jim Martson, which is a photon a soliton? Now, that's a good question. Okay, I think definitionally, a soliton is that single wave. If you get a single bump, that's a soliton. If you go look in a dictionary definition. Although I think Bill uses the same label to describe the actual, say, electron, right? That a soliton is like a vortex kind of thing, or a donut shape. I forget exactly what that is. That comes out of the cannons and things like that. Now, me personally, you can call it that, but I don't think that that's particularly a soliton. So I would say a photon is a soliton because it is a single bump, right? That's how I see it. And so David points out that, the ether is one solution and not the only one. So there are lattice and particle models as well. And certainly there are other ways of describing the medium, I guess. But there's just completely also different ways of describing whether what's fundamental. Like Bill thinks the electromagnetic field itself is fundamental, and in that case, there isn't necessarily an ether. There's just field, right? Let's see here. Yeah, Bill, I have you live, so if you have any comments, please let me know. And I'm going to add Dennis in here as well. So we're just going to go over comments here. Unfortunately, because I was going over that presentation, that I wasn't looking too much at the comments. So we're going to spend some time going over the comments here. So let's see here. So we have had some technical difficulties here, though, unfortunately. Ian is having problems getting into the system. At present, I can see you and turn on camera and sound. And I see Harry's here. So you could only get you on YouTube, that the others didn't work, and that the YouTube had poor resolution. And of course, Harry thinks I need to be replaced because I don't know what I'm talking about. And obviously, I don't understand the basics of the basics of EM theory, and this discussion is ridiculous. Well, of course, Harry, we welcome your opinion here. And let's see here. We have some private chat here. So let's see here. So people are saying there's an echo in the audio. So are you guys getting that, Bill, Dennis? Is it still
When
echo?
Bill talks, I get an echo when I talk.
You get an echo when you talk.
Yeah.
Yeah, I can hear that. That's probably maybe a headphone thing. Sometimes you can get away with it, but other times you can't.
I don't have any headphones, and Bill isn't wearing any either.
Let's see here. So Bob says that he tried YouTube and he couldn't enter any comments. So I'm seeing the comments from YouTube, so I think we're probably okay there. But I'm actually kind of curious how many people are actually on YouTube. So in my view, I can only see one person, which is a bit concerning. I'm thinking that there should be more people than that. So, but Bob asks, why is there a private chat and live comments? I can't enter live comments. Now, live comments are things that are coming in from YouTube and Facebook. And then the private chat is the 6 people who have joined me in the live.naturalphilosophy.org. So if you want to send a specific comment just to me, you can try putting that in the chat. But of course, I have to be paying attention to see whether anyone's written anything. Otherwise, I might generally ignore that because there's not say a flag or something that becomes immediate obvious. But I suppose I need to just keep on monitoring the icons. Like I just got a new comment from Ian. Okay, apparently you need to be registered with Google before being able to submit comments. Okay, that's a helpful feature. So good to have here, Ian. And if you want to join us live on the program and talk, then you just go live. So I see that Harry is here. So Harry, I'm going to add you on here. And we should be able to hear you talk. So if you would like to express your opinions on how I don't know anything, then, feel free. Are you there, Harry? Well, we have him there. Now we are getting a bit of an echo. Like I said, if you have headphones, it's usually a good idea. So I'm going to put on my headphones here, see whether that improves things any. Okay. So hopefully that I'm not hearing much of an echo going on. So is that better for people? Bill? Dennis?
Can you hear me?
Yeah, I can hear you, Dennis.
No echo now.
No echo now. Okay, so that was my fault. Sorry. So I should wear my headphones. All right, so I see we have Harry here. Hello, Harry. Welcome. How you doing? So we're not hearing you if you're saying anything. Your picture doesn't seem to be moving either. Maybe your internet connection is a little bit slow.
It's not.
Oh, well, we just heard.
I could. The only one that I use that worked was the only on the I tried this new. I don't know what's going on.
Yeah, we're trying this new thing out here. I think your audio is breaking up. I think it might help if you turn off your video because it seems to be very bandwidth limited. Yeah, why don't you try turning off your video and
do anything.
Can't do anything? Well, there's a little icon on the bottom there. It says stop
I can't do anything. I've got a blank screen.
It completely blanked out on you?
Responding.
But we
Well,
hear
at
you
least
very
at
well.
least we can hear you now. You're not cutting out.
Blank screen, but I can hear you. It's weird.
Okay, so we're gonna move on, I think. So that was our first little segment there on polarization. So Dennis, you said you had to you have some comments on photons, Dennis?
That's right.
Okay, why don't you go ahead?
Tom Phipps, who did experiments as well as theory, told me before he died that their photons can't be correct because the U.S. Navy has a ultra low frequency transmitter with it, transmitters with, and the antennas are cables laid offshore, and each antenna is several hundred miles in length. And to reach the submerged submarines because the ocean water is conducting, so you have to go to extremely small, low frequencies to avoid the ocean water absorbing the photons, as you were pointing out, if there are photons. But if you do the math, with an antenna that long and a wavelength that long and a frequency that low, it doesn't make any sense that there are photons for that particular radio hookup between the naval commanders and their submerged submarines.
Well, I would agree with that in the sense that I think radio waves are a very different thing than light waves. So my position on that is that you've got this submarine transmitter, and it is in fact creating this kind of pressure wave, which is very, very long, and very much like a sound wave. That's very much, I think, what's going on. But what we have as a photons are created as the specific result of electron activity around atoms. So the thing that's coming out of the submarine antenna definitely is not a photon. What's coming out of the submarine antenna is a very long radio wave, which I think is a compression phenomenon.
The transmitter is a long wave, but the receiver, you can't have on a submarine an antenna that's several hundred miles long. So the submarine does not have the same type of antenna as a transmitter that's laid offshore in cables.
Well, my point is that photons can only be generated by electrons around atoms. So it's absolutely true that the submarine transmitter is not generating a photon. But that doesn't mean that photons don't exist.
No.
So I would say that photons exist as these individual, we were discussing what a soliton is, and that I think is like a single wave that goes up and down like this. If you're measured on a oscilloscope, like that. Or it's like an explosion wave, right? You fire off an explosion, and a big pressure wave comes off, goes whoop, and the energy is delivered in one big boom, right? Those, I think, are like solitons, and those are what photons would be like. If you could create a radio transmitter that just delivered spikes, I guess that would be closer to what we would call a photon is, right? So I think, and I'm not 100% sure, but I think it's just easier to think of photons as like being like the soliton, which is the single wave, right? And that the radio wave is the same phenomenon, but the radio wave happens sinusoidally and is totally continuous. So, Dennis, you had another comment.
Yes, if you consider that an electron is a soliton, or a toroidal ring, however you want to describe it, then you can see that the waves emitted by them have to be transverse. That's because if it was spherical, then you'd have and it was transverse, then you'd have a vector field, namely the electric field, that was continuous all around the spherical electron at transmission time. But that's impossible by a theorem in elementary topology. On the other hand, if you have a toroidal ring, it can generate transverse waves. In fact, it's easy because if you have a vector field on a continuous vector, non-zero vector field on a toroidal ring surface, then you can, there's no contradiction from topology. And since the magnetic field is supposedly at right angles to the electric field, you can have both simultaneously on the surface of a toroid, but not on the surface of a sphere. So from the viewpoint of toroidal or soliton electrons, the waves, they certainly can and easily do generate transverse wave packets, like what you identify as photons.
Well, I guess that brings up the whole question of whether we even need transverse waves. I suppose you're saying that you had the toroidal ring, and that was the thing that I was looking for, because I know that you and Bill also assigned that name to solitons.
He used the solitons, but that's a special case of a toroidal ring, I think, except that a toroidal ring, I assume, it has charge rotating inside it, whereas Bill doesn't need the charge for his, as I understand his theory correctly, he doesn't have the charge in the center of his soliton in the toroidal ring.
Yeah, but it's the key thing here is a toroidal ring structure, which
that's key, yeah.
Which I disagree with completely.
Uh-huh.
So my point of view is that the electron itself is in fact completely fundamental, that it can't in fact not be made out of individual negative charges, because if it were made out of individual negative charges, then you have to put something in there to prevent those negative charges from repelling each other.
Well, the magnetic pinch force, the charge is rotating.
You have to
the
come up
magnetic pinch force contains the charge. Exactly, it's in equilibrium in Dick Bergman and my model.
Like I said, you have to come up with that. So your model has these three little things inside. I think you call them strings, and you have to invoke the magnetic field. But then you have to explain what the magnetic field is. And in my theory.
Wait. Why do we have to explain what the magnetic field is? In logic, any logical model has its undefined terms. It has to have at least one undefined term.
But the magnetic field is a really complicated thing. It's not a simple thing, the magnetic field. To take the magnetic field as fundamental, I think, is not something you can do. That's kind of my disagreement with Bill, is that you can't take something as complicated as the electric and magnetic field, which have to be simultaneously available, and call that fundamental. See, now the problem why you have to be able to explain the magnetic field is because they have alternate theories, like my theory. Let's see, I'm getting some echo back here, which say that the magnetic field is actually a polarization of the ether particles. And if that were the case, then the magnetic field is literally not available at the level of an electron, right? The magnetic field can only be available outside of the electron itself. Inside the electron, the magnetic field itself cannot be available. So that's why it's important to be able.
The magnetic field inside is there because the charge is not just a circle; it's a ring. So as the charge moves around, it's more dense towards the center of the circle of symmetry of the toroid. Which is as you go around, you have circles no matter how you go around, and the locus of all the centers of those circles is itself a circle, but it's at right angles to all the circles at the point of an intersection. So that there's charge all the way through the toroidal.
Yes, I mean
electron.
there's no arguing that there's charge there.
So whenever
question
there's
is
charge,
what-
there's a magnetic field. So the magnetic field has to be inside too, not only outside.
No, not necessarily. No, that doesn't follow actually.
Yes, it does, because otherwise you can show that it wouldn't be in equilibrium using electrodynamics.
See, this is the key: is that if you have a theory, like my theory explains how the magnetic field is mediated, right? And that theory says that the magnetic field cannot possibly be available at the level of the electron. That's going to break down. That at the level of electron, individual electron, because the electron is the actual source, the mediator, the thing that creates magnetic fields, it itself cannot use magnetic fields.
Well,
That's kind of my logic and why I would disagree that is almost circular, I would guess. And this is why, to be complete, you really do need a precise description of how you think the magnetic field works, so that then you can apply that and provide a complete picture of why that magnetic pinch is available. But if right now you have to say that the magnetic field is just fundamental, that it's just there, it works according to the known existing laws and works down to the level of electrons, which might be possible.
inside electrons, even.
Yes, inside electrons. But you're making an awfully large postulate there, that the magnetic field is there, and you can't explain the magnetic field, because that's always going to be kind of an embarrassment with your theory, that when they ask you, well, how does the magnetic field work, and you can only say that
it comes from moving charge.
it's fundamental.
It comes from moving charge. That's
Yeah, but how does it come from moving charges? What about the moving charge builds a magnetic field, and then when another charge comes through that field, causes it to deflect? I mean, that's a very complicated physical reaction that you just can't say is fundamental. I mean, that's really complicated.
Well, I don't know. I mean, how simple do you want things to be? I mean, the universe is complicated.
I think the universe is not complicated. I mean, the only way.
But as I mentioned before, the trouble with your model of the electron is that it's not really very computationally effective.
It's computationally.
I mentioned this one before. It's sort of like in the old days, they thought the Earth was on a huge turtle, because that explained why the Earth moved around the sun so slowly, and yet it was very heavy, so that the shell of the turtle was strong, so it could withstand the pressure of the Earth, and it moves slowly around the sun. You see, and that explained everything to people, but it's not computationally effective.
Why wouldn't it be computationally effective? Because I'm just saying that the electron is fundamental. It has the properties that we know about. You can compute anything you want with Coulomb force law. And that's the only thing I'm saying. I'm saying that the electron is fundamental, that you cannot break that thing down.
You can't break it down into further pieces of matter. That's true. But you do have to break it down into fields.
Yes, and that field would be the spherical field, although you would disagree with that. I mean, I need to see some experiments that show that this field is not spherical. I know there are some experiments saying that electron might have, say, a fundamental spin or actually a fundamental magnetic field or something like that.
Yeah, it does.
I
It has
am not.
spin magnetic moment, and it has magnetic field. It has an electric field, and it has energy and so on. All this was cooked together by Dave and myself, and it's out there if you're interested in common sense science.
But I don't get the comment that you don't think that that's computable, because you have all those
It doesn't help you
things.
compute things. Let me explain what you can compute from the Bergman-Allen model. All right. So now, suppose you ask yourself, well, what if this circling a very small radius toroid, well, it's the outer radius is much greater than the inner radius. There's two radiuses in a toroid: the small radius and the big radius. And so, if you can ask yourself, well, what kind of waves? What if the toroid began to sort of wave, standing waves on it, wouldn't that cause certain types of fields, EM fields, to be generated and cause loss of energy in the toroidal electron? Well, you can attack that problem computationally if you do things the way we do, or even also in case of Bill's model, he can compute things. Or you can say to this, well, what if there were several modes, like it could wave around as it goes around, but also it could contract and expand. The small radius could be a sinusoidal thing in time. Well, you can compute that too. It's not easy, but it can be done. But if you assume it's just one thing, like a bell, then you can show it 1 over r squared maybe, and a few things like that. But to get into more esoteric computations, it's just not useful.
Well, I would challenge you in that. Are those esoteric calculations relevant to what happens in the real world?
Yes, I would. Either that or the model is completely defunct. Yeah.
Because
But
you
your
mentioned
model, it doesn't really matter because you can't really compute any esoteric things. So why worry? Just like, the people used to think there was a turtle. You can't compute anything, but using that model, but you have to go to like Kepler's laws to compute something, or even the Potomac system.
Well, you mentioned that you could, for example, calculate the transverse wave coming off a toroid, and certainly I think I could see that happening. However, I would argue that the transverse wave doesn't exist. That what you're really looking for is something like a compression wave. Now, in my theory, that's a little bit iffy. What kind of wave would come off? I don't know, like a sphere.
It depends on its frequency. If it was a bell, you'd hit it, and it would have a certain frequency.
Yes, exactly. That's exactly what I think it is.
But then it stops and starts right there. What about all these other more esoteric considerations? If you look at the spectrum of the sun, for example, there's all these little bumps in the spectrum analysis. And each one of those is, either some hydrogen atom, just the electron presumably changed from one orbit to another, and so on. With a Bell model, you just kind of like, well, it's just a bell, it's just a bell.
Well, that's just the basic functioning of the electron. If you're talking about spectra, then you have to explain why is it the electron only takes integer distances away from the atom.
Yeah, right? Well, there's some guy by the name of John Eric something or other who claims that he can do that. I believe it's him anyway. He can do that because it's really continuous waves, but they interfere in a certain way, which leads to since the interference isn't registered on any instruments, it looks a lot like photons.
Well, that has to do with the nature of the actual electromagnetic field itself. So I don't feel that the electromagnetic field itself is in any way fundamental. I feel it's just like you have a bell and you're striking it, and it's putting out this certain particular frequency and phase, and that is actually what the electromagnetic field is. So that's why I would say that the electromagnetic field is not fundamental. It's actually a physical compression wave, and that's how I see how the electromagnetic field is mediated. All you need is just some media, some particles or something to represent those waves. And so I'm just starting from the electron. I don't feel that, I mean, I'm just trying to understand your point there. If your main objection is that, we can't play all these mathematical games with electron, it's like, well, I think you might be, playing with yourself, that you really don't need to. You can come up with all these interesting things, like, I could take any arbitrary object and say, well, I can compute all kinds of weird things on this thing, but it may not actually have any actual relevance compared to,
I know, but
say, a sphere.
Consider the turtle example. That doesn't give you the same sort of information that the Potomac system gives you and the Kepler's logs give you.
Well, the thing is that the problem with the turtle is that it's what I would call a little green man, in that it's something which is completely made up, something for which we have no actual physical experimental evidence for. And lots of people do that.
Well, the evidence was this. This turtle shell is hard, so it will support the weight of the Earth. And two, turtles move slowly, so therefore the Earth was on the back of the turtle would move around the sun slowly. So that
but it is in fact a little green man. It's something which has no experimental verification. Now, if you went and you put a spaceship out into the solar system and you saw the turtle, then that would be experimental verification. But since we've put spaceships out in space and we've taken pictures of the Earth and we have not seen this turtle, then we can conclude that that's not the right idea.
Yes.
But now in the case of the electron, now this is something which is, a settled science, basically. Everybody agrees electron exists, and it does, it has got this electric field around it. And
that's true. Santilli, for example, with his hadron theory, I don't believe he has any electron.
Well, he would be in the minority.
Yeah,
I think
that's right.
The vast majority of everybody would agree that the electron and the positron and the proton, some people don't think the neutron exists, but we can have general agreement on those things.
Yes.
So I'm just expressing my viewpoint. I mean, all viewpoints here at the CNPS are valid, but we're trying to discuss things and perhaps maybe convince people one way or the other, because we're never really going to make any progress as long as nobody agrees on anything. If everyone just sticks on their own theory, no matter how implausible, then we're just going to sit here and go in circles, really. So and that honestly is mostly what we do. It's like, I express my theory, you express your theory. Nobody ever budges at all from their existing thought. So my only hope is that there's someone out there watching who might be influenced and might want to join one or the other camps. Someone who doesn't have a dog in this fight. But it's just really difficult to convince other people that, for example, if I try to convince you that your toroid rings don't exist, that was a complete imagination, that's just going to be a hard sell, right? I'm trying to sell you that the electron is just this fundamental thing, right? Now you can criticize.
If you can show that the Bergman-Allen ring model leads to an incorrect prediction, then I'll have to junk it.
So an incorrect prediction, right?
Yeah,
well, probably one incorrect prediction would be is that if it was not fundamental, and we've done lots of experiments on electrons, we've never found 3 of anything inside of an electron. So that in itself contradicts the Bergman model.
Oh, no, it doesn't. Come on now. Right.
I mean, we would have found it, I think, right? Do you
So
agree we
a
would have found it?
discharge is considered as an ideal gas. There's positive gas and there's negative gas. It's not an object to be found in. It's an ideal gas, if you like.
Well, another prediction would be if the toroidal ring has a very specific symmetry, and you have to be able to distinguish between which one of those things is like what's a positron and what's an electron.
Yeah, that's
from what I understand, it has something to do with the orientation there.
No, and, the positron has a positive charge circulating, and the electron has negative charge, and they both have the same mass.
Yeah, but what distinguishes those two? I mean, I have a positron,
well,
I have an electron.
Positive charge, and one has negative charge.
Well, that's belaboring the obvious, but what is the difference? What makes the difference? Physically, there must be something making a difference.
Positive charge and negative charge, when they're brought in contact with each other, emit energy. They disappear. They cancel each other.
And how does that happen? I mean, that is a functional description, but not a physical one.
Well,
I mean, everyone can say that. That's just like, opposites attract. But why? What causes two particles to just spontaneously, accelerate towards each other out of their own volition? How does, that's not something as a scientist you can just postulate.
Laws say that unlike charge attracts.
Well, yeah, like I said, we know that, but there needs to be a fundamental explanation for why that happens. That's what scientists do. We not only just observe.
Undefined terms.
And like I said,
Allen theory, the undefined terms are positive charge, which is sort of an ideal gas, and negative charge, which is also an ideal gas, and the two, when they combine together, emit energy, EM radiation of some kind.
Yeah, and that's what I said, as a criticism, is a pretty not fundamental thing to be fundamental.
Well, Einstein, who I don't, worship like most scientists, but Einstein made a very important point. He said things should be as simple as possible, but no simpler. They should be
so
as simple.
So if I could show you, for example, an actual explanation, actual physical explanation for why electron and positron should be pushed together, then would that be a better explanation than just saying that it just happens, right?
Well, for example, consider Newton's theory of gravity. He did not know what gravity was. He just didn't know, and he admitted it. He knew how to.
That's lacking in that, and he would have explained it if he could.
His theory of gravity is what's used in the space program, not Einstein's. His theory of gravity is why their satellite, their one spaceship, went all around the solar system and came back, and was the difference between prediction and what occurred was 6 feet.
Well, there's no question about that. But as science, we still should need to know how gravity works, because if we knew how that works,
everything as scientists, we should know everything.
Yeah, but the goal is to be able to explain how charge works. Because if we knew how gravity works, then we could possibly engineer ways of defeating it. But since we don't know how gravity works, we have no way of defeating it, right?
Morton Spears has a theory, which I elaborated on in my first book, of electrostatic gravity. Gravity is basically electrostatic in nature.
Yes, and that would be an example of how to explain it. I mean, personally, I agree with that. I think gravity is just totally electrostatic.
Yeah.
And with that knowledge, we could defeat gravity.
The fact that Newton did not know how gravity worked didn't keep him from being able to predict, using his theory, if he only had a computer, that the spaceship could go around the solar system and come back, and the difference between prediction and actuality was 6 feet. Now, he didn't know what gravity was, but it wasn't the end of the world.
No, it wasn't. But I think that at the level that we're trying to work at, which like we were trying to explain, I don't know, like how electrons are what electrons are, and how atoms work, and things like that. We do need to know how the magnetic field works, how the electric field. I mean, not only how they react, but what is the physical mechanisms behind it.
Yeah, the physical mechanism is the thing we don't have. We do know pretty much how they act. Although Wesley has his own electromagnetic theory, which I go for pretty much.
But that's kind of my
no,
point.
we do not know at this point how the magnetic field comes from moving charge. We just know that it does. Just like Newton didn't know how the gravitational field propagated through empty space, but it did.
Well, I think that is one of the things that we discuss. I mean, that is an active topic of discussion in probably almost all of our talks, actually. There are people who are trying to figure out, how exactly these things work. So it's certainly for us as dissidents an open topic of discussion. And if we can figure it out, we're all going to we'll be famous and have the Nobel Prize or whatnot.
Well,
that is certainly an open topic of discussion.
I don't think the Nobel Committee will go for anything that falsifies GRT, Einstein's general relativity. It's too
No, I think anything
embedded.
that we come up with should confirm the measured experimental results.
That's right. If you can't predict honest data, which is hard to come by nowadays, but if you cannot predict honest data and you get the wrong prediction, as I mentioned the other day, and you do in the case of classical mechanics, you can't handle nutation properly, then you have to say that the theory is falsified and there's something wrong with it. But that doesn't mean it's useless. It just means you've got to be very careful of when and how you apply it.
Yeah, well, that's getting back to a main point here, which is that there are some things which are okay to postulate, and then there's some things which I would say are very complicated. Like if you can't explain what your positive cloud is and what your negative cloud is, I would say you're missing something very fundamental, that there's still something very incomplete about your explanation.
Well, I would agree with that, but the thing is, the trouble with your Bell theory is that you can't really compute too much from it. Whereas at the toroidal ring thing, you can compute all sorts of things from it. Now, if some of these computations turn out to be wrong, then you'll have to be real careful when applying the theory because it may not give you the right answer. But so far, that hasn't happened.
Well, I would guess that my response to that would be that really the only thing you have to be computationally aware of is the electric field, which is emitted out of the electron, which is simple Coulomb's force law, and that's really easy with a sphere. So that's the only computation that I see as being really relevant here.
Well,
anything else you may have computed may be like counting the number of angels that can fit on the head of a pin. It's like, you can do that, but
computationally effective.
The only computational effective thing we need to do is be able to predict the behavior of electrons, right?
Yeah, then their radiation and how they interact with each other, and in the Bergman-Allen model, we have a model of a proton too, and a model of a neutron, which is a proton, which is smaller since it's more massive. It's like a ring inside a ring. And they're rotating in opposite directions, but since the proton has positive charge, the electron has negative charge, it then follows that the currents are in the same direction, although they're rotating in opposite directions. Then what about the neutrino? Isn't that in there too? No, because the two rings mutually spin pump each other according to Ampere's original experiment. That is to say, if you have a circular wire and you got current in it, and another one near it in the same plane and so on, maybe a little bigger in diameter, then it will cause current to flow in the same direction in the larger one. And conversely, if you have it in the larger one, it'll cause current to flow more rapidly in the smaller one. So then you get mutual spin pumping, which then adds to the energy of the system. No energy is not conserved here. And so, but that extra energy is known to exist. So they postulate a neutrino to get rid of it.
All right. Now I see we have some other people in the wings here. I see James. James is here. Good morning, James, or afternoon, wherever you are. Let's see. You have to turn on your microphone so we can hear you. I'm going to unmute your mic here. Oh, their mic isn't connected. Okay. Well, we could see you there, James, a little bit there. Let's see here. So if you want to say something, wave at me or something so I know. Okay, so Bill wants to join the conversation. Okay, Bill, go ahead. We have some comments.
First of all, I want to say that experiments have been done on the toroidal ring in all kinds of fluids. And the characteristic of a fluid is, whether it's air or water or electric field, is it has a tensile strength that keeps it together. And so in all of the known fluids, the shape of the soliton is always a toroidal ring. And whether it's a smoke ring or a ring in a thing of water, or it's a ring in the electromagnetic field. And so you have that, and there, this toroidal ring has two types of motion, I guess you would say, in the field. It has a motion around the circumference, and it has a motion across the cross section of the ring. So the spin is the one across the cross section of the toroidal ring, and the magnetic moment or magnetic field of the electron is around the circumference of the ring. So the electron is made of that, and in the theory of elementary particles, which I have published based on the soliton, all elementary particles are composed of combinations of soliton rings. Then the combinations can vibrate, and the minimal vibrational energy is the rest mass of the particle. So in the case of the theory of elementary particles, the 96 elementary particles that all experimentalists agree exist, can be, all the properties of those can be predicted from the properties of the soliton and soliton structures. So for instance, the electron is composed of 3 solitons. The solitons all have they're all similar, and the vibrational energy, the minimal vibrational energy, is what we call the rest mass of the electron, and it can be predicted to 8 significant figures, and it can be predicted for all of the 96 different elementary particles. So if one has a competing theory, one must be able to predict all these properties. The standard model of elementary particles cannot do that. And so, and particularly it cannot do it to 8 significant figures. And then
now we do have a question for you, though. Do you see the question on the screen?
Yeah.
So Stefan has a question. He says that the vector and scalar potentials are not real, according to you. But he says that they do have experiments to prove that they're real. Now, I'm not 100% sure what he means about scalar vector potentials.
Where is this? Oh, here it is on the screen. Sorry.
Yeah.
Okay. The vector potential is says that there's no such thing as a magnetic monopole. That's what the definition of the vector potential says. But the Chinese have been selling millions and billions of magnetic monopoles, and I have a few hundred in my house. And you probably have some if you have refrigerator magnets at your place. Uh, and you can easily determine by the experiment that they are magnetic monopoles. And these are refrigerator magnets. And so if you have the kind that looks like a dark brown sheet of plastic that is on the back side of something that's on the front side, you can take the.
But I suppose that Stefan is pointing out that there are experiments that prove that they're real. So I mean, I suppose that's one way of.
If I have one experiment that can show that a magnetic monopole exists, it invalidates the vector potential because it says del dot A equals 0. That means there cannot be a magnetic monopole. That is the definition of the vector potential. So if the fundamental definition is false, there is no such thing as a vector potential.
Well, I guess that's the answer, Stefan. Let's see. Now, there's another comment here. So I'm going to have to cut things a little bit short today because I do have another thing that I need to go to. So let's just finish it off with, say, this question here. So an important question about magnetic effect, in my opinion, is relative to what a charge should move for it to generate a magnetic field. And, of course, that's an interesting question. So if you are an aetherist and you think space is filled with some physical substance, then I think it's relative to that physical substance that it should move to generate a magnetic field. So in that case, there would be a sense of absolute motion and not maybe all of this relative stuff. In my own opinion, I think space is filled with like a dipole substance, and when the charge moves relative to those relatively stationary dipoles, and it causes all those dipoles to basically point in the same direction as the moving charge, and that is what actually mediates the magnetic field. But it does give you a definite thing for it to be relative to. Okay, so like I said, I think we'll need to wrap things up here, and I thank everyone for participating, and even Harry. So this is what Harry has to say. So don't pay any attention to what I say. That's what Harry says. Just to let you know. But Harry, we love you. Hopefully, you'll be able to get your system working so that we can, hear you and see you. Okay. Because there's always got to be one guy who's just like, disagreeing. So otherwise, if it's all just a love fest, this is no fun. So, but that will do it for today's broadcast. And if you have any comments about how this worked, please send it to us. We're considering these different systems. If it didn't work for you, let us know. If it worked for you, let us know. But we're still playing around with this. So until then, see you later.